Okay, so welcome back. And now let's talk about the deformation in case of an existing structure. Okay, so the deformation of an existing structure at which its performance should be evaluated can be estimated from the inelastic design spectrum. Okay, you can use the inelastic design spectrum to compute the deformation on the existing structure. Of course, the actual structure can be a multi-degree of freedom system, but our discussion today is only limited to the idealized single degree of freedom system. And also there is a way how to idealize a multi-degree of freedom system into an equivalent single degree of freedom system. So what is carried out in the assessment of structures? The initial elastic vibration period, the Tn, and the yield strength, Fy, of the system is determined first based on the properties of the structure. For example, the dimensions, member sizes, design detail, for example, reinforcement, reinforced concrete structure, steel sections, connections, and so on. So once you obtain these two properties, for a system with a known value of Tn and damping, so once we know the Tn and we know the damping, we can obtain the pseudo acceleration from the elastic design spectrum. So remember that this is not a Y, this is from the elastic design spectrum. You can obtain this from the elastic design spectrum. You can obtain then Fy if we know Ay from the inelastic design spectrum. Or, sorry, we just revert this. Since this is the assessment, so we have to go systematically. We obtain the elastic vibration period and the yield strength. With the known vibration period and the elastic damping, we obtain the pseudo acceleration using the elastic design spectrum. We can obtain Ay using the equation that Ay is equal to Fy divided by W over J. So let me write here. It's just like the way the base year coefficient is obtained. So you know the yield strength of the system, divide that by the weight in G, you can obtain Ay. So once Ay and A are obtained, we can calculate the yield strength reduction factor Ry, that is equal to A divided by Ay. So using this equation, we know how much yield strength reduction factor is available in our system. Corresponding to this, Ry and Tn and the ductility, for example, you know that we have the relationship between Ry ductility and the Tn. So if we know these, the vibration period, if we know the strength reduction factor, we can obtain the ductility factor. Okay, so this is known, we can obtain this using the available equations. For example, that of the new mark, Ry, when it is related to ductility, is 2 mu minus 1 square root, or directly to the ductility, depending on what is the vibration period. If vibration period is less than Ta, reduction factor is just 1. If Tn is greater than Tb and less than Tc prime, okay, or if Tn is greater than Tc, so we can use these relations to obtain the ductility factor. So uh, you have to rearrange these equations for the ductility and obtain ductility given the Ry. Once these are known, you can obtain then the, so we have this, and from the ductility then we obtain the maximum displacement demand on that single degree of freedom system. And the equation that we can use for the maximum, for the peak deformation demand in case of the inelastic system is equal to ductility, and then the Tn divided by 2 pi square into Ay. Okay, so Ay we already have Tn by 2 pi square, that represents the omega, 1 over omega, into ductility, and this gives you the maximum displacement, peak deformation demand. Once you know the peak deformation demand, you can compare this with the capacity of the existing structure system to comment on whether the system is exceeding the capacity or if the demand is less than the capacity. So if the demand is less than the capacity, the system is safer, or in case if the demand is more, then that will represent the failure of the structure system. So this is one way of computing the peak deformation demand on the structure system, knowing the properties of the structure system. There is another way, and a very interesting way, that is also incorporated in a number of computer programs, that is a graphical method. But it's essentially the same like the previous one, but this graphically shows what is happening. So in the graphical methods, there are 2-3 procedures which are available in this. There is a procedure known by Pfeiffer. There is a procedure that is given by Chopra, and there is another one that is given by Ryan. So there are 3 different procedures available which can be used for the computation of the inelastic displacement demand on the system. And they are quite appealing in terms of presentation, as well as for practical application for assessment of structures. So in this procedure, the inelastic design spectrum, which is the standard AY versus TN format, is converted to the AY versus D format. So what is happening here, let me just write here. In this procedure, what happened, we know that the classical acceleration spectrum, which look like this, okay, with the time period or with the vibration period in seconds, it is converted to another spectrum where acceleration is on the x-axis. This is acceleration divided by g, and there is a displacement on the d, or you can say is d. So there is a displacement on the on the x-axis. So what is happening that at every vibration period value, the acceleration is converted to displacement, okay, by using the pseudo relation. So d is equal to a divided by omega n square. So the relationship something look like Okay, if we close it, this is the, let me just do it in another way. Okay, so in order to be more clear, this acceleration. So when the displacement become constant, so it will have a drop like this. Or if there is no, so it will just keep on increasing. So anyway, now in this case, the it may be in inches or it may be in millimeter, centimeter. Now in this case, the on x-axis there is displacement and on y-axis there is acceleration. So it is this standard design spectrum that is converted to the ADRS. This is known as the acceleration displacement response spectrum, ADRS spectrum. The peak deformation of the system is determined in the next step. The peak deformation is obtained like we know the ductility of the system, we know the vibration period of the system, and we know the yield displacement of the system. We can obtain how much mixing displacement demand will be acting on the system. Okay, the resulting data pair AY and D are plotted to obtain the demand diagram for the inelastic system. So this is also known as the demand diagram. This ADRS is also known as the demand diagram. Okay, and if you see here in this case, the vibration period was on the x-axis, while in this plot, the radial lines are basically representing the vibration period. Okay, these radial lines they represent the vibration period. So during assessment, what is done actually? Let me just start here. The capacity of a system is also drawn on the same demand spectrum. Okay, but the capacity which is generally given in terms of the yield strength and the displacement, the yield strength is divided by the weight of the system. So the results are represented in terms of the AY by G. For example, let's say if the yield strength of a system is equal to 0.225W, in terms of the base year coefficient AY by G, it will be shown as 0.225. So all the values of the y-axis of the capacity curve, for example, if we have a capacity curve like this is displacement, this is force. So it goes like this, let's say. So this force, which may be Newton or kilonewton, is divided by the weight in order to convert it into AY by G. Okay? So then you can plot that curve. Okay, so what you see, this red line, this the blue is the demand diagram, and this is the capacity curve. Okay, so you can see that the capacity curve intersect the demand diagram curve for a reductivity value. If you look at this capacity curve, it is intersecting the demand curve at this point. Okay, but remember this diagram, demand diagram, is obtained for a number of ductility values. Okay, so you can have, let's say, a curve like this. You can have a curve like this. You can have a curve like this. Okay. The first one is with the ductility is equal to 1, and the others are for the increasing value of ductility. So, for example, 2, 4, 8, and so on. Now, for every curve, what you need to do is to obtain these intersection points. Okay? And in every case, you have to compute the ductility demand on the system. So, it's, let's say, the ductility demand on the system Knowing this point and the yield displacement of the system, because the yield displacement is there, you can obtain from the capacity curve, you can obtain the ductility value for a number of these cases. So when the ductility demand on the system becomes equal to the ductility demand of these demand diagram curve, you stop at that point. And then that basically defines the actual deformation demand on your system. You can just read from there what is the displacement demand on that particular system. Okay, I hope you got my point. Okay, let me just show you this procedure graphically. Okay, this plot is showing you the elastic design spectrum. There is elastic, but there are a number of other design spectrum obtained for various ductility values. For example, ductility 1.5, 2, 4, 6, and 8. And you can see that when you increase the ductility, how the design spectrum is changed. Okay, so in this case, you can see a normalized design spectrum that is normalized to the value at the 0 vibration period. Okay, so what is done in the graphical method of the assessment for the existing structure is that the spectrum is converted to the ADRS. Now, this is the acceleration displacement response spectrum that is also known as the inelastic demand diagram. So in the inelastic demand diagram, you can see acceleration on the y-axis and displacement on the axis. And as I mentioned, the radial lines from this common point 0 from the origin indicates the vibration period. So what you need to do is to draw the capacity curve of the structure system on these plots. So this dash line you can see is basically the capacity curve of our single degree of freedom system. If it's a real structure, so what you have to do is that you have to convert the capacity curve from a multi-degree of freedom system to a single degree of freedom system. So then you draw these, you have these inelastic demand diagram for a number of ductility, and you look at the intersection points. And you will see that one of the intersection point is exactly giving you the same ductility that of this spectrum. Sometimes if it is not working exactly, so either you can revise the inelastic demand diagram or you can interpolate in between these two. For example, in this case, this point is giving us the ratio of this displacement to this displacement exactly equal to 4. And the curve is also with having the ductility is also the one developed for the ductility 4. So this is what you want. So in this case, the ductility demand on the structure system is 4. Once you know the ductility, then you can obtain the peak deformation demand on the system using this equation. Let me just go there. Okay, you can obtain the peak deformation demand on the system. You can directly obtain from, well, let me just go here. You can directly obtain this the deformation demand graphically from this either or using the equation, but this is better you can use directly from this equation. And so you can compare this with the behavior of the system, okay? Whether the demand is more than the capacity and what will happen to the structure, whether it will be in a slight damage or a moderate damage or a heavy damage or whether it will be collapsed in a given, in that particular earthquake. Okay, now let's talk about the inelastic deformation ratio. These two procedures, they are quite useful and practical applications, but there is another useful way of representing the peak deformation demand on the system, and that is through the inelastic. Okay, give me a break of 5 minutes. I'm going to change my position. Okay, so the other important information is the inelastic deformation ratio. Let me just mention here. Inelastic deformation. Okay, you can use the previous two procedure in order to compute the peak deformation demand on the system. But you can see that there, in some cases, we are using the pseudo relationship to convert the acceleration to displacement. But in case of the inelastic deformation ratio, you can directly obtain the ratio between the inelastic deformation and the elastic deformation, which are basically the obtained through the response analysis. Let me just mention here. Okay, the screen is not shared. Let me share that. Okay. So this ratio of the inelastic deformation is more relevant to the assessment of existing structure with the known ductility or with the known yield strength. And since the 1990, there has been increasing emphasis on estimating the structure deformation on in the displacement-based design, where these informations are important. So let me just mention here. Okay, so this deformation ratio is either represented by C mu that is equal to the peak deformation demand of the inelastic system to the peak deformation demand of the elastic system for a known ductility. Okay, and it's also represented by CR that is equal to UM by U naught, peak deformation of the inelastic system, to the elastic system peak deformation for the system with a known yield strength or yield strength reduction factor. So one is this known ductility and the other is the yield strength reduction factor. So let me just quickly go to those figures. Okay, so here you see is the median estimate of the Cu or the Cr for the various values of ductility or for the various value of the strength reduction factor. So for your structure system, if you know the ductility or if you know how much strength reduction is applied on your system, you can use either of these plot. You can use either this or this to calculate Cu. Because if you know the Tn, so just take that value and read the Cu. Okay. So just like the previous cases, what is important here is like in the short period range, there is a huge variation in the peak deformation demand in comparison to the peak deformation demand for the elastic system. But as you keep on going here and you reach to this range, to the velocity sensitive region, they are almost the same. So the equal displacement rule apply. Both the peak, the inelastic and the elastic displacement are the same. In this case, you can see some reduction in the inelastic system in comparison to the elastic system, but later on, beyond the TF, you can see that they are almost the same. And as I mentioned, that in this range, we always assume that they are exactly the same. Okay? But here is certain equations are required in order to accurately compute the inelastic deformation demand. The same is also in terms of the reduction factor that you can see. Okay, you can see almost similar behavior. That beyond the TC they are the same. There's some reduction here, but again it gets equal to the value of the elastic values. And in case of the reduction factor, you can see that just like the unlike the ductility, a small reduction can cause a huge variation in the strength. Okay, and this indicates that the relationship between the ductility and the strength reduction factor is not the same. So like 1.5 ductility is not equal to 1.5 strength. You can see that there is a huge variation, particularly at the short time period. But when the vibration period is longer, these two becomes equal because they produce the same effect in the inelastic deformation demand. The same is also shown for a number of earthquake records, for ensemble of records, for values for record like LMSR, LMLR, where the LM represents large magnitude and S represents shorter distance. And here, large magnitude and long distance, or again, short magnitude, small magnitude, short distance, small magnitude, and large distance. And if you plot these values, you will see that they are not dependent on the magnitude and distance value. They are almost the same. Okay, and even if you look at these again, the peak value in terms of for different soil, again you can see that the behavior is exactly the same. There is very minor change when you move from various type of soil, but the in fact the behavior is independent and it remains exactly the same for the peak deformation demand in comparison to the elastic demand. There are variation, in fact, if you are using a near fault ground motion or a far fault ground motion. Like this black one is for the far fault ground motions, and these two are for the near fault ground motion. One is fault normal and the other is fault parallel. So fault normal is more severe as compared to the fault parallel. But these are the value when they are plotted for the Tn. But if Tn is normalized by the Tc, which is Tc is the is the corner period of the acceleration spectrum. If you divide by them, you can see that now they get closer, and you can see that apparently there is no any uh, difference, and they are exactly the same. So we can see that the median value of the C mu or Cr they are exactly the same for various type of ground motion. They are independent of the near field, far field ground motion, and they are independent of the magnitude and distance. But this plot is showing you that it is dependent on the shape of the response spectrum. So if you are using just spectrum with the TN, then you have to pay attention, and you can see that they can be affected by the type of accelerogram used for the assessment, whether it's a far fault ground motion or whether it's a near fault. Okay, again, you can see, look at the behavior of the CR. Again, the peak value of the deformation ratio when the strength reduction is applied. So again, you can see variation in the near field and the far near fault and far fault condition. But when you normalize them by TC, there is no difference. So anyway, this was all from my side. I will give you this lecture so that you can read them again thoroughly. But this was, I think, almost a short lecture to talk about the inelastic response of the system required for the design of the system and also required for the assessment of existing systems. So if there's any question, you can let me know. Otherwise, I'm done from my side.
सर इंफॉर्मेशन कौन से बुक से आपने लिए बिल्ड करने के लिए
Again, ये आप दोबारा बताएं, Ruhul, I cannot hear you properly.
सर ये इंफॉर्मेशन जो है आपने कौन सी बुक से और जो चोपड़ा बुक है या नईम
हाँ,
की बुक है
एग्जैक्टली, आप चोपड़ा के बुक जो है उसका मेन, दिस इज योर मेन टेक्स्ट बुक, तो आप उसको रेफर किया करें फॉर मोर डिटेल। और बाकी जितना भी क्लास में डिस्कस हुआ है तो उसके लिए क्लास नोट्स वी विल प्रोवाइड ऑल द स्कैन, तो आप वहाँ से रीड करें।
थैंक
ठीक
यू
है,
सर
क्लास नोट जो इट इज़ इनफ फॉर यू। ओके, लेकिन अगर आप इन डेप्थ आपको चाहिए इंफॉर्मेशन, देन यू शुड रेफर टू दी चोपड़ा's बुक।
और दूसरी सर पिछली क्लास में जो आपने जो वैल्यू निकाली हुई थी फर्स्ट जो आपने रेफर किया था कि ये टेब में निकालना है तो कहानी सर अगर कोई अच्छी लिंक या वीडियो वगैरह बिल्कुल रिलेटेड इसी के साथ क्योंकि मैंने सर्च किया लेकिन वो
मुझे बिल्कुल समझ
फुल
नहीं आई। कैन यू
सर
बी स्पेसिफिक, आप क्या कह रहे हैं?
सर ये पिछली क्लास में सर आपने न्यूमेरिकल किया था न्यूमेरिकल
यस।
इसमें सर आपने जो डायरेक्ट वो वैल्यू दिए थे मूड शेप की मूड शेप और वाइब्रेशन पीरियड की
यस।
तो सर ये शेप में या टेब में हम किस तरह करेंगे इसके लिए कोई इंफॉर्मेशन चाहिए थी
Well, it's a very simple exercise. I think we can do it. The first thing that you have to do is to do the model analysis, and then for every mode you have to read the displacement values. So it's like in a SAP when you do the mode analysis. So for every mode, it gives you a deflected shape, and so for that deflected shape, you have to read the displacement values. Then you can normalize them. So
ओके
uh,
सर
I think it's not that difficult. You can do it yourself, or sometime let's see in future if we are working on some design problem, so I can teach you the same how we can do it.
ओके सर थैंक यू सो मच
Okay.
थैंक यू सर
Okay. Good. Okay. So let me just close this now.